Hey everyone, welcome back to another video, and today we will be doing the inverse of Laplace transform. So without further ado, let's go to our first example. Hi everyone, so this is our first example of today's inverse Laplace transform. So we have here f of s is equals to s plus 1 cubed over s to the 6. And our very first step is we want to expand our numerator. So if we expand this cube function, we will have s cubed plus 3s squared plus 3s plus 1. Okay, now subbing into our f of s for the expanded version, we have s cubed plus 3s squared plus 3s plus 1, and everything here is over s to the 6. And then now we want to break down the fraction. So we have s cubed over s to the 6 plus 3 times s squared over s to the 6 plus 3s over s to the 6 plus 1 over s to the 6. Now we want to simplify each of these fractions to make our calculation easier. So we have 1 over s cubed plus 3 over s to the 4th plus 3 over s to the 5th, and then we have plus 1 over s to the 6th. Now, after breaking it down into its own fractions and simplifying each of the fractions, now we have the simplified version, and we can just take the inverse Laplace transform for each of these fractions here. And when we're taking inverse Laplace transform, we need to refer back, most of the times, we need to refer back from the Laplace table. And so which property is appropriate for taking the inverse Laplace of each of this fraction? And in this case, recall that we know that t to the n is equals to n factorial over s to the n plus 1. However, wait a minute. We do not have a factorial here for each of these, right? We have 1, we have 3, we have 3, we have 1. So, we need to manipulate this property to make it more appropriate to use for taking each of the inverse Laplace transform for each of these fractions. So now we have t to the n dividing both sides of the equation by n factorial. Now we have t to the n over n factorial equals to 1 over s to the n plus 1. Now, this looks way better because we do know that 1 over s to the n plus 1 is similar to each of these fractions that we have here. Okay. Without further ado, let's take the inverse Laplace for each of these fractions here. So we have the first one, inverse Laplace of 1 over s cubed, plus we can pull out all of the constant or coefficients here by the identity of Laplace transform. So we have s to the 4th plus 3 times inverse Laplace of 1 over s to the 5th plus the inverse Laplace of, I'm gonna move this so we have more space right here. Move this over here. 1 over s to the 6. Okay, we are set and ready to go to take the inverse Laplace for each of these fractions that we have here. So for the first one here, we do know that 1 over s cubed is the same as saying 1 over s to the second power plus 1. So we know that we're gonna use 1 over 2 factorial times t squared. 2 factorial is just 2, so we can put that as 1 over 2. Now, plus 3 times 1 over 3 factorial times t to the third power, or cube, plus 3 times 1 over 4 factorial times t to the fourth. And lastly, we have 1 over 5 factorial times t to the fifth power. And so simplifying our final answer here, we will get 1 over 2 t squared plus 3 times 1 over 3 factorial, or 1 over 6, is just 1 over 2 t cubed, plus 3 times 1 over 4 factorial. 4 factorial is the same as saying 4 times 3 times 2 times 1, which is just 24. So 3 over 24 is 1/8. So we can write here 1/8 simplified version, t to the 4. And we do know that 5 factorial is just 120. So we have here 1 over 120 times t to the fifth power. And that's how you solve inverse Laplace transform. Hi everyone, welcome back. So this is our second example of today's inverse Laplace transform topic. This time we have a function of f of s is equals to s over s squared plus 3s minus 4. First thing that we need to notice here is the denominator. We have an quadratic function. So most of the times when we're doing inverse Laplace or Laplace transform, we can do factorization. And so we do know that if we do factorization on this fraction here, the denominator will be s plus 4 and s minus 1. Sorry, yes, minus 1. Now we have s over s plus 4 times s minus 1. Now, we can see here that it has something to do with partial fraction decomposition. So our very next step is doing the partial fraction decomposition, which is s over s plus 4 times s minus 1. And everything here is equals to a over s plus 4 plus b over s minus 1. Okay, now when doing partial fraction decomposition, we just need to find the values for a and b. And to do that, we just need to multiply each of this on its own. Or we need to do cross multiplication. So a with s minus 1 and then b with s plus 4. So we now have s is equals to a s minus 1 plus b times s plus 4. And let's expand this out. So we have s equals to as minus a plus bs plus 4b. Now let's group all the a and the b that has an s, and also a and the b that doesn't have an s, or they're just constants basically. So we do have here a plus b times s plus minus a plus 4b. All right, now we can set this a plus b is equals to 1 because the coefficient of s here, or the variable of s to the 1 power, is just 1. And for our second one, we have here negative a plus 4b is equals to 0 because we do not have a constant on the left hand side right here. And now we just need to solve this system of equation. What are we going to use here? We can use substitution or elimination, but this is fairly easy because we can cross cancel the a directly by using elimination of addition here. So if we do that, a plus negative a here will be 0. There you go, that's gone. And now we have b plus 4b, that's equals to 5b, and 1 plus 0 is just 1. Therefore, solving for b here, we'll get 1 over 5. And then when we solve for a, we just need to substitute this b value into either of this equation. And I'll choose the first equation, which is a plus b equals to 1 right here, because it is an easier equation to use. So we have a plus 1 over 5 equals to 1. Therefore, our a is just 1 minus 1 over 5, which is 4 over 5. All right, we solve for a, we solve for b. We just need to substitute both of these values that we got, a and b, into this partial fraction decomposition that we started with. So now we have 4 over 5 over s plus 4 plus 1 over 5 over s plus 1 minus 1. Now, after doing all of these steps, we get the value of a and b. We just need to take the inverse Laplace for each of them. So when we're taking the inverse Laplace for each of them, we do need to know which Laplace table property that we're gonna use. And we do know that if we have a e to the at here, this is equals to 1 over s minus a. Okay, this is perfect, because when we take the inverse Laplace for each of them, we can just pull out all of the coefficient outside, or all the constants here. So we have s plus 4 plus 1 over 5 times inverse Laplace of 1 over s minus 1. And now taking the inverse Laplace of the first one, 1 over s plus 4. We do know that this is s minus a, so therefore our 4 will become a negative here. So we have, therefore, our solution will be 4 over 5 e to the negative 4t plus 1 over 5 times e to the t. And that's how you solve inverse Laplace transform for this particular function using this property. Hi everyone, welcome back. So this is our third and last example of today's inverse Laplace transform. So we have here another function. We have 6s minus 12 over s times s plus 1 times s squared plus 1. If we see this like our previous example, we do know that we need to do partial fraction decomposition as we have a quadratic function at the bottom. So now doing the partial fraction decomposition, we do have a over s plus b over s plus 1 plus c times s plus d over s squared plus 1 because this part is not factorable. And so after we break it down using the partial fraction decomposition, which we want to find or solve for our a, b, and c, and also d to be able to take the inverse Laplace transform for this one here. And so doing that, we now have 6s minus 12 equals to a times s plus 1 s squared plus 1 plus b times s squared plus 1 plus cs plus d times s plus 1. Okay, now let's expand the right hand side of this equation. So now we have 6s minus 12 is equals to as cubed plus as squared plus as plus a plus bs cubed plus bs plus cs cubed plus cs squared plus ds squared plus ds. I know this looks a lot, but it will look easier after this. Take a look at this one. We do know that we have a here, or a constant with no variable attached to it, and we do know we have a negative 12 there. So we know the value of a is equals to negative 12. Now we need to gather all the coefficients with s to the third power or the cubic power, and also s to the squared power, and also s to the first power, to the first degree. So now we have three different equations. The first one is a plus b plus c equals to 0. We have a plus c plus d equals to 1, 0. And lastly, we have a plus b plus d, and that's equals to positive 6, not negative 6. Using this information, we do know that a is equals to negative 12, so this makes everything easier. Doing that right here, we have b plus c equals to positive 12 because we add the 12 both sides of the equation for the first equation there. And then the next one we have c plus d equals to positive 12 as well. Now lastly, we have b plus d is equals to 6 plus 12, which is 18. Now we need to solve all of this equation right here. And to do that, we can use the augmented matrix using the Gaussian elimination. We can also use elimination. We can also use substitution. But in this case, it is easier to use substitution. So right here, what we have here is b plus c equals to 12. And so let's set this equation into a c equal equation. So we have 12 minus b. After we set that into a c equals equation, we know that we can substitute the c into the second equation right there. And doing that, we have now 12 minus b. Let's do it right here. We have 12 minus b plus d equals to 12. Adding 12, subtracting 12 both sides, we have here minus b plus d equals to 0. Now we have that as 0. We now have two equations that we can use elimination on. This is the first one right here. As you can see, we only have b and d now, only two variables, and we also have b and d on this equation right here. So using eliminations for both of these right here, we have b plus d equals to 18, negative b plus d equals to 0, and we want to do elimination with addition, so we cross out the b's. B plus negative b is 0, d plus d is 2d, 18 plus 0 is 18, therefore our d here is 9. 18 divided by 2 is 9. Now we get d here, that's 9. We want to sub this d back inside our equation right here. We can use that equation or we can use that equation. It doesn't matter which one, but I'm just going to use with the one with the 0, so it's easier. So we have negative b plus d, or 9, equals to 0. Therefore, b is equals to 9. Okay, we have b, we have d, we have a. Now we just need to find c, and this is fairly easy. Why? Because we have all the components, and if we're just left with one variable and we have all of the other variables, or we have all of the other coefficients, it will be easier to get. Now let's use one of this equation right here. Let's use this equation right here, c plus d equals to 12, to solve for c. So using this equation right here and substituting the value of d equals to 9, we have c plus 9 equals to 12. Therefore, c is equals to 12 minus 9, which is equals to 3. Now we have solved all of our variables, or our a, b, c, and d. We just need to substitute all of these values, a, c, d, b, back into our partial fraction decomposition at the start. Okay, doing that, we have a as negative 12, so we have negative 12 over s, plus b is 9 over s plus 1, plus c is 3, so that's 3s, d is 9, 3s plus 9 over s squared plus 1. Now, we have solved our partial fraction decomposition. Our very last step is to take the inverse Laplace transform for each of this function here of our partial fraction decomposition. So for the first one here, we can just set this into negative 12 times the inverse Laplace of 1 over s plus 9 times the inverse Laplace of 1 over s plus 1 plus the inverse Laplace of 3s over s squared plus 1. And there's a reason why I split the fraction here into 3s over s squared plus 1 plus 9 over s squared plus 1, because we want to use two separate properties or identities. And I almost forgot, we can pull the 3 outside to not complicate the inverse Laplace there. So we have 3 times the inverse Laplace of s over s squared plus 1, and our last inverse Laplace is going to be 9 times the inverse Laplace of 1 over s squared plus 1. Okay, we are all set, and we just need to take the inverse Laplace for each of these. But before we start taking the inverse Laplace transform, we always do need to know which property or identity that we're going to use from the Laplace table. And we're going to use 4 identities here. The first one is 1 is equals to 1 over s. And the second one is e to the at equals to 1 over s minus a. And then we're going to use cosine of at is equals to s over s squared plus a squared. And lastly, we're going to use sine of at equals to a over s squared plus a squared. All right, we have all of our identities that we're going to use, and I'm going to bring it down here so it's easier to track and see. So now using each of this. So for our first inverse Laplace transform, we directly know that we're going to use this first property right here. So this is going to be equal, or our final answer is going to be negative 12 times 1 over s. So that's just going to be negative 12 over s. Plus, the second one is going to be 9 times the inverse Laplace of 1 over s plus 1. We're going to use this property right here. E to the at equals to 1 over s minus a. Therefore, we're going to have 9 times e to the negative t. Okay. And our third inverse Laplace transform right here, s over s squared plus 1, and all of you may guess that we're going to use the cosine, and you are all right. So we're going to use the cosine a of t. So now we have 3 times cosine a squared here is just 1, and we can square 1, it will still give us back 1. So we have cosine of 1 times t, or we can just write it as cosine of t. Last but not least, we're gonna use sine a t for our last inverse Laplace transform right here, 1 over s squared plus 1, or 1 over s squared plus 1 squared. So we have here 9 times sine of 1 times t again, and we can just simplify that into t. Therefore, that is our final solution for our third example of doing today's inverse Laplace transform.